Right, okay, welcome back to the second discussion on the subject of optics. And today we will just explore another way of thinking about optics and the paths light may take. And this comes from Fermat. So Fermat was after Huygens, I think, but they, I believe, were relatively close together historically and just had slightly different ways of thinking about things. But this is, again, one of these things which forms a, it's part of any physics degree. Certainly first year physics will encounter this within their optics modules. And so I think it's useful just to be aware of a different way of thinking about the same problem. And Fermat brought together a principle of least time. And what Fermat hypothesized was that the actual path a light ray takes between 2 points is actually the path that takes the smallest amount of time. And whilst we discussed Huygens constructions, which seems a very odd way of looking at things, in some ways this is a bit nicer because it's just a bit easier to think about. Although it's worth stating this still doesn't answer any real fundamental, it doesn't provide any fundamental explanations for what light is or how it moves. However, it is just another way of thinking about these problems. Just as an example of this, so if light is moving at a constant speed, then the least time will be equivalent to the shortest distance. So if we look at the example, we have a starting point for a beam of light in position A and a final point in position B. We have 3 different options given by the red path, the green path, and the blue path. And so within this particular example, it's moving at constant speed in this medium, which is most likely air. But within this example, the light would, by Fermat's principle, the light would take the green path because this is the shortest distance. So the light has taken the least time moving in the green path. This is something which we've already realized instinctively just from how reflections work in mirrors, where you can measure the sort of distances between your 2 different points in the reflection. But Fermat was mainly just coming up with a theory which could explain this. But the theory is of use as well, because even though you can have different mediums with different optical densities, so all of these air to glass, etc. transitions, which we discussed yesterday, but it's worth also considering this from Fermat's point of view. And when there's a difference in speed, so we know that as light enters something which is a greater optical density, the speed at which it travels is slower. So if we look at, again, an example, 3 different options from light traveling from point A to point B, it can either be just the shortest distance, red, or it can be some different distance. So it's a longer distance now, but spends a longer time, or longer distance, sorry, within the first medium before then changing direction in the second. And the insight this provides is, of course, the actual speed light is moving in medium 1 isn't the same as in medium 2. So there's actually different speeds it's moving at. And this then tells us that if we consider the overall time of each of these lines, it is not necessarily the one which is the shortest distance. And so this then tells us that light will bend at these interfaces between different medium or media. And so in this case, the green line is again the quickest path in terms of time between A and B. And this gives us this familiar observation of this refraction effect. Thinking about analogies for this, and so something which Fermat is unlikely to have used when explaining it to his students. If you imagine we have a lifeguard who's on sand on a beach, and they spot a swimmer being threatened by some sort of shark or something. If they actually were to want to save this person and get there in the quickest time possible, this isn't the shortest distance, because they can run faster on the sand, but then when they swim, it takes more time. They have to stretch out the amount of time they spend running at a higher speed on the sand before then entering the water to swim at the slower velocity. The difference, of course, between this example and light is light will automatically do the fastest time path, whereas in this example, the lifeguard is actually making some sort of calculation and prediction based upon their experience in which is going to be the shortest amount of time. And one of the nice things about Fermat's principle is, because it involves properties which are actually, well, essential within physics, so speeds, definitive angles, time, also these refractive indices. What this means is it actually can form a much more rigorous mathematical proof than Huygens construction, which takes assumptions into its own workings. And again, this is something we're not going to go into, but you can actually solve these equations from Fermat's principle, and then this actually arrives at the familiar Snell's law. And so the reason I'm bringing this up is because it's always nice when you have two different approaches, two different starting points, and when they arrive at the same final conclusion or equation, that's very good to reinforce our confidence that that is a good way of modeling this. The other thing which is useful about Fermat's principle is that it's very clear that these optical paths are reversible. So the previous movement of a beam of light from this first point into this second point, if you have the light moving the other direction, it will follow exactly the same path. Okay, so that's all well and good. So let's now move on to critical angles and total internal refraction. So we've already seen numerous examples of refraction. So as something is moving from an optically more dense medium into a less dense one, we get some deviation of this angle, which brings it further away from this normal. But at very great angles, so very large angles of incidence, we then have this phenomena where the light is actually completely reflected back into the initial medium. And so this is total internal reflection. And as implied, because it's total internal, this means all of this light remains in this medium and there actually isn't any escaping at all. And between these two examples, so we have a small angle, which gives us refraction, a much larger angle, which gives us total internal reflection. We then have a critical angle. And so this critical angle is the angle where the refracted ray is at 90 degrees. And so actually is going right along the boundary between these two materials. This critical angle is given the symbol of theta with a subscript c, which makes sense. So it's nice to have something which we can actually relate to in physics. And we can then already spot that to have total internal reflection, our angle theta must be greater than this critical angle. So the critical angle is therefore telling us the point at which above that angle, you will then have total internal reflection. Similarly, when your angle is smaller than the critical angle, you then have refraction, as we covered yesterday. In terms of calculating it, again, we go back to Snell's law. So n1 sine theta 1 equals n2 sine theta 2. However, we know for the critical angle that theta 2 is going to be 90 degrees. And we also know the sine of 90 degrees is equal to 1. So if we know the sine theta 2 is equal to 1, this means n1 multiplied by the sine of the critical angle is equal to n2, which is then this equation highlighted in red. Rearranging this for theta critical angle, theta c will be equal to n2 divided by n1, all to the inverted sine function. And so that is how to arrive at your equation for critical angle from Snell's law. And so with that in mind, quickly onto some questions, as we were all pretty strong with these yesterday, I thought. So we have 3 different surfaces or interfaces between 2 different materials, if you like. So first of all, we have a glass to air transition. So in this case, the refractive index of this particular glass is 1.52, and air is, of course, 1. And so the first question is, what is this critical angle? Second of all, we have glass to water. So now, instead of the air being n equals 1, we have a water second interface, which is n equals 1.3. And then finally, we also have a diamond to air transition. Diamond, of course, having a quite substantially large refractive index of 2.42. So if you could all try these calculations to see what you get as your critical angles for each of these 3 surfaces. And so, as I think people are hopefully comfortable with, the critical angle for the first surface will be equal to the inverse sine function of 1 divided by 1.52, which is equal to 41.1 degrees. And this also tells us that you cannot have total internal reflection moving from anything of a lower refractive index to a greater refractive index, because this number would be greater than 1, and you cannot have an inverted sine function of a number greater than 1. So I could have put one of those questions in to be sneaky, but I didn't. So just to put these answers up, so the first one is 41.3 degrees glass to air. If you then were to have a glass to water, you've got a smaller difference between these refractive indices, and as a result, you've got a greater critical angle. And then for diamond, which seems to be one of my favorite things at the moment, we also have a very great difference between these refractive indices, and because of that, the critical angle is relatively small. That's 24.4 degrees. And just looking at diamond in a bit more detail, what this actually means is that because of this critical angle of 24.4 degrees, it means a beam of light will not escape the diamond unless this angle is less than 24.4 degrees. So if you imagine your beams of light entering your diamond shape. It will then simply bounce around inside the diamond until it has a smaller angle of 24.4 degrees, and then that light can escape. And this relatively small critical angle is one of the things responsible for, to our eyes, diamonds looking all shiny and sparkly. So in some senses, they trap the light inside themselves very well, and then it takes that light longer to be emitted. And so to our eyes, a diamond would seem brighter than things around it. And this is the principle by which, I mean, I'm not going to go into discussing jewelry in in too much more detail, but this is the reason why things like the actual cut of a diamond has been developed. So they over experimentation, they've learned how to play with the angles and the ratios of how to cut a diamond gem to basically show off this aspect of the material. And it's something I've always noted, but as humans, we seem attracted to things which are very shiny, and also things which are inert, like gold and diamond are quite useful because they don't degrade in their quality. But it's interesting to explain this just from an optical point of view, or at least I think so.